Hello there, my name is Mike Raftery and I'm a partner with SCM Connections. And thanks for joining us today. We're going to go through a quick video here on the IBP supply optimization engine. This is going to cover time series supply, so no order series. It's going to be used for rough cut capacity planning and what if scenarios. So here's the network we're going to show. In this case we have customers sourced to regional DCs, and then all of the plants they're the DCs, and then all the plants can actually source all of the distribution centers. This is a great optimization problem because it'll look for least cost, open capacity. Basically it'll look for the absolute minimum possible cost to meet the demands coming from those customers through those distribution centers, no matter what the occasion. So you can have downtimes, you can have weekends, third shifts, doesn't really matter. The optimizer will look for those least cost options to find it. So let's go ahead and jump in. In this case we see the consensus demand, and the consensus demand here is about 5,000 each. But let's go to the master data first. So the customer source is showing these customers here are being sourced each from a single location, just like we saw in our diagram. And that customer sourcing ratio is 1 or 100%. That means when you run a heuristic, there's only one sourcing option possible for that customer to be sourced for our product here, IBP 100. Now the optimizer can look for different options, but in this case we are single sourcing it, saying that each regional customer is coming from their local DC. But IBP 100 can be sourced just from one, and every other product that we're going to show has the same. Now in location source, what you'll see is the similar relationship, where you have, but there's more options. So product 100 for source for locations 60 to 10, it can be sourced from any of these three locations, any of them, and that's because they are three records here. Now for a heuristic or just a supply-demand match, it'll use the straight ratios. So location transport ratio here you'll see is 0.3, 0.3, and 0.4, because I didn't really feel like rounding, and it just makes it easy. So you can see when you run a heuristic it goes 0.3, 0.3, and 0.4. Now the optimizer doesn't work that way. The optimizer will just see these as potential sources and look for the least cost option to meet those demands. So it'll see all three of these as equally likely to source the supply. In this case from 100 to location 6710, optimizer can pick any of the three choices, but the heuristic will go 0.3 to 1010, 0.3 to 1310, and 0.4 to 1710. Now the production source header, you'll see it has a source ID that's required, so it shows you how it's going to make each one of those. So let's go ahead and jump in. So you can see the customer demands here are, like I said, 5,000 each. Just to make it easy, everybody has equal demand, and you can see with the heuristic run, they're met all the way across the board. Equal demands, equal, it's just saying this is the consensus demand that's being fed into the optimizer. Now any shortages would show up here because you're actually shorting the customer demand, not internal demands per se. So if I move now to the DC to customer demand, this is now saying which DCs are supplying which customers. And in this case you can see it's 1 for 1. Everybody's fat and happy with a heuristic. It's a just straight supply-demand match. There are no constraints on it whatsoever. Now to look at those ratios, what they do in a heuristic run, we can go to the transportation side, and you'll see here it goes 0.3. Or if you look here, my ratios are just slightly over here, 0.3, 0.3, and 0.4, which means that 1010 gets 0.3, 30% of demand, 1310 gets 30% of demand, and 1710 gets 40% of the demand when running your heuristic, which is what we're doing here. And if you look at this graph, you'll see same things. In this case it's 1720, but it doesn't really matter. You can see the proportions are straight across the board. Again, the heuristic just executes the data that's out there. It doesn't really do any sort of thinking about capacity, which is where we're going to go next. You can see nice even bars, and it's important to note this because it's going to contrast with what we do when we run the optimizer here in just a few minutes. See, a whole horizon, just perfectly straight, perfect scenarios. nothing about the capacity. Now when I go to my production view, you'll see the same thing. That demand is passed straight to the production locations, and because there's no constraints, there's no capacity, there's no limitations, straight supply demand match, you get, guess what, evenly distributed production quantities. That same production quantity for 1010, if I put a filter in there, you can see it's the same ratio across the board because it's just following your master data. I'm kind of belaboring the point, but it's important to notice that these segments are there because it's going to contrast to what we do when we run the optimizer. Now when I run my capacity, you can see that it seems to be okay, except the fact that I have put a downtime here in the beginning of calendar year 2018. You can make up, whatever reason you want, extended holiday, capital downtime, vacation, maintenance, whatever, doesn't matter, or even seasonality. Now the important part is that you can see the production ratios here are the same, which is fine, except the fact it didn't actually solve my problem. So in the weeks where it gives the same proportions of capacity usage whether I have capacity or if I don't have capacity. So if you look at the capacity utilization in the down weeks, there's no supply. You can see that there's no supply because it's red. It's 999% because it's using capacity that does not exist. Again, it's not really doing any intelligence, it's just following the math. My master data said 0.3, 0.4, 3.4 to all the production sites, so it followed it. This is up to now a human to solve, if you're using heuristics. The humans would move production around, they would put in production adjustments, so on and so forth. And if you look at the inventory spread, this is an inventory target, projected stock. You can see everything looks fine, right? My inventory and my inventory targets are the same. My productions and my demands are the same. But it doesn't matter because it's not really feasible. Okay. Now let's go to the inventory costs. So the inventory costs show what goes into the optimizer. You can see there's a non-delivery cost rate for product 100, an inventory holding cost rate of 50, an inventory target violation cost rate of 100, and these are all incentive costs to get the model to actually solve these problems in an efficient manner. So the highest cost is a non-delivery cost, holding cost rate is 50, target violation or safety stock violation is 100. Basically making it really expensive to short, making it somewhat expensive to violate safety stock, a little bit more expensive to hold inventory. Transportation is the same. Now the interesting one that I've done here to kind of add a little bit of flavor to the optimizer problem is I've changed the production cost rate. So what I've said is that for the same products, 1010 here is the cheapest, 1310 is the next cheapest, oops, still on target violation, and then 1710 production cost rate is the most expensive, meaning that if all things equal, it's always cheaper to fill up 1010 first, the capacity there, then fill up 1310, and finally fill up 1710. Now the optimizer will make all these adjustments and figure out, okay, based on the capacity I have, the downtimes I have, and these production costs, what is the least costly way for me to satisfy as much demand as I can, maybe not all of it, but as much demand as I can, with the capacity that I have. And it's going to try and satisfy as much of it as it can because the non-delivery cost rate is the most expensive. So it's going to try and get rid of all the non-delivery costs first, and then it's going to try and get rid of all the inventory target or safety stock violations second, and then it's going to try and reduce my inventory holding costs third, and then it'll do that by maximizing the available capacity against the production costs. And if you look at the capacity, this is the problem that we're going to solve. So a human, like I said before, they could always move things around, but the optimizer does it just quite a bit faster. So we're going to go here and run the optimizer and see what we come back with. Now it should take those costs into account. I'm going to select my optimizer for the planning units and give it a run. Alright, so we've run our optimizer. You have my status log here showing that it's finished. Yay. No errors. And so let's see what it did. We'll work our way back here from capacity. Now if you look, we had a downtime here which give us some capacity problems. I'm going to refresh after the optimizer run, and look at that. The optimizer also respects your constraints. So it saw that there was no capacity there, and it filled up all of those resources accordingly. And even more importantly, if you notice, it filled up 1010 first, then 1320, and then 1710. So it followed that cost structure that I had just pointed out. 1010 was the cheapest, so it's always going to fill up first. Then the next one, 1310 is the next most expensive, so it's going to fill that up next. And then finally, it is going to fill up 1720. And again, it's doing that to make sure that it's the least possible cost solution overall. And if you look at that, there's no bucket where it's using 1710 capacity where 1320 is not also fully utilized. So if we go to inventory, what did that do? Well, let's take a look. In order to meet those inventory targets, it's going to have to make some compromises, and it's going to compromise by carrying inventory, and you can see that's what it does right here. So you have your downtime that I put in at the beginning of 2018. So what did it do? It built my inventory levels up to cover for this downtime. You can see there's no blue bars here, meaning that there's no production. So it built inventory ahead of time, anticipating that short fall in capacity, and then it brings it right up to that line, and then it carries on its merry way after that. The point being is here that the optimizer saw that downtime, and it accommodated for it by an inventory build. Now the question is, how did it accommodate it? And that's what we're going to look at next, is to say, well, all right, it built inventory, great. How do I know that it's the most efficient way to do it? Well, if we look at this capacity here, you can see that it's completely full. It's completely full, just short of it, but if you go to the production, you can see, okay, well, what did it make? Well, it made a whole bunch of different products in different ratios. If you remember, our heuristic run had 0.3, 0.3, 0.4. This is anything but. It's showing you not just that it's making products in different weeks, but it's making those products in different plants. So it's actually looking at the plant capacity, looking at the holding costs, looking at the different production volumes, and saying, well, this is the most efficient way for me to make, in this case it's just product 100, but each one of these products will have a different set of variables in terms of what it makes. And transportation would be the same thing. So if we look at, okay, where am I getting product from? It's not split evenly across all the source plants. My distribution centers are now receiving products from different locations across time, depending on a least cost model in anticipation of that shortfall. Again, this is all stuff that humans could do theoretically. We did it here in about a minute, maybe, with the optimizer, and at the absolute least possible mathematical cost. So all this math isn't anything magical, it's just looking through all the possible combinations and seeing what you can do. Now if we look at where the customer is, now the customers are getting supplied, the DC to customer ratios are getting supplied at different rates, and even anticipating some possible shortfalls. I don't think there was any in here. We'll take a look. Yeah, it looks pretty good. So what did it do? The optimizer looked at the costs that I had, and it built that inventory ahead of time, and we can see that it did it quickly and efficiently. And now I have a solution that's viable for me to bring to an S&OP meeting or a capacity planning meeting, so that I can actually show some options in terms of, well, if we do want that downtime at the beginning of 2018, here are the volumes we're going to look at, here are the different plants that are going to be supplied, here's the transportation volumes on those lanes. All the supporting documentation that you would need is right here in front of you, based on a fully optimized cost plan. Now all those optimized plans are based on human input, so there's still room for error, but given the inputs that I showed you, this is the absolute least cost plan to accommodate my downtime. And we did it here with SAP's IBP application in about 10 minutes. Pretty powerful tool, pretty great analysis. Thanks for joining us. Again, this is Mike Raftery, and we will see you on the next video.